If you want to know what the cloud actually looks like, don't look up at the sky.
Real.
Look at like a 2.5 million square foot concrete bunker in suburban Virginia, one that consumes more electricity than the entire country of Iceland.
It is wild when you actually put it into perspective.
It really is. You know, we use words like wireless, virtual, ethereal to describe our digital lives. And I think it creates this expectation of total weightlessness.
Yeah.
Like the AI you use to draft a report is just, I don't know, floating out there in the ether, completely detached from the physical dirt under our feet.
It's a very comforting illusion, honestly. I mean, we've essentially trained ourselves to think of technology as something that has, well, successfully escaped physical constraints.
Right.
But the reality of the modern internet is the absolute definition of heavy industry.
And in the age of artificial intelligence, that physical weight isn't just heavy, it's growing at a scale that's, frankly, almost hard to wrap my head around.
Oh, absolutely.
Which is exactly what we are digging into today. For this deep dive, we have a really fascinating stack of sources. We're looking at a thesis called COA-002-NOVA01, which completely redefines how we observe urban structures.
Yeah, it's a brilliant text.
And we are pairing that with two incredibly dense analytical frameworks, the LMOS model and the MCP, or Membrane Contact Phase model. So our mission today is to cut through the relentless hype of the AI boom.
Which is everywhere right now.
Everywhere. We're going to apply what our sources call cognitive cooling, just lowering the heat of our immediate hyped-up reactions so we can calmly observe the hidden, massive physical infrastructure that actually makes our digital lives possible.
It is such a vital shift in perspective. I mean, if you want to understand the bottleneck of our technological future, you have to stop looking at the software algorithms and start looking at the ground.
Okay, let's unpack this, because changing how we look at the ground means changing how we look at cities themselves, right? Usually when we think of a city, we think of, I don't know, its culture, its skyline, maybe where it ranks in population. If we strip the map away, how should we actually be looking at cities through this new lens?
Well, we need to adopt what the sources call the City Observation Architecture, or the COA perspective.
The COA.
Right. And the COA doesn't care about a city's tourist attractions or its restaurants or, its square mileage. Instead, it observes cities strictly as concentrations of civilizational functions.
Civilizational functions. Okay, so we're talking about looking at a city based purely on what it does for the rest of the world.
Precisely. I mean, think of modern human civilization as a massive, globally distributed biological system.
Okay.
It isn't spread evenly. Specific vital functions concentrate in highly specific local areas just to achieve scale.
Right, because you can't have everything everywhere.
Exactly. We're talking about the generation of capital, the circulation of physical logistics, the coordination of governance, human living systems, and, crucially for our era, computation.
I want to make sure I'm visualizing this correctly. If you picture the globe like a giant computer motherboard, a city isn't just a collection of buildings and roads. It's a very specific component soldered onto that board. So like one city is the memory bank, storing global capital.
Yeah.
Another is the data bus, moving physical shipping containers around. And another city acts as the CPU, doing the heavy math.
That is a highly accurate way to frame it. And it highlights a core rule from the LMOS framework we're analyzing today, which is structure over impression.
Structure over impression.
Right. What's fascinating here is that we are constantly bombarded by the impression layer.
Oh, yeah. The flashy announcements of new generative AI models.
The CEO keynotes, the stock market rallies, all of it.
Yeah.
But the LMOS framework demands, we look past that to the underlying operational system, the OS layer.
Okay.
The OS layer is the physical, heavy, institutional reality that actually moves the needle.
But wait, I have to push back on that a little bit. Doesn't the impression actually drive the structure? Like, if developers didn't hype up AI to the public and to investors, the billions of dollars in funding wouldn't exist to build the physical structure in the first place, right?
Well,
Doesn't the narrative have to come first?
Impression absolutely allocates the capital. You are totally right about that. The narrative directs the money.
Right.
But structure determines if the math actually gets done.
Oh, I see.
You can have $1 trillion in funding, but if you don't have a physical power grid capable of handling a gigawatt load without melting down, your AI model does not exist.
Wow. Yeah.
Computation is not abstract. It requires an incredibly specific, very rare set of physical conditions to function.
Which brings us to the ultimate case study for this structural reality, Northern Virginia.
Yes.
For those who follow the tech world, Silicon Valley gets all the movies and the fame.
It's the face of tech.
Exactly. But Northern Virginia, often just called Novel, is essentially a quiet, sprawling, suburban region outside Washington, D.C. You don't see Netflix dramas being made about the startup culture in Ashburn, Virginia.
Definitely not.
Yet, it has quietly become the world-leading hub for computational infrastructure.
It is the ultimate computation factory for the global motherboard. And the reason it's concentrated there, rather than somewhere cheaper or maybe more famous, is crucial to understand.
Right, because why not just build it anywhere?
Exactly. You can't just buy a massive warehouse out in the desert, stack thousands of GPUs inside, and call it a data center.
Right.
High-level computation requires a massive convergence of what the texts call constraint membranes.
Let's break down that term, because membrane usually makes me think of, high school biology, like a cell membrane.
Yeah.
Why use that specific word for a city's infrastructure?
The biological analogy is actually entirely intentional. Think about what a cell membrane does.
Okay.
It creates a boundary that protects the delicate internal workings of the cell from the chaotic, fluctuating environment outside.
Right, keeps the bad stuff out and the good stuff in.
Exactly. It regulates what comes in, like nutrients, and what goes out. In urban terms, the physical infrastructure acts as a membrane for digital capabilities. The delicate servers doing the computation cannot survive the chaos of the raw physical world. They need perfect temperature control, uninterrupted power, and total physical security.
So the city's power grid is a membrane. It filters raw, volatile energy into a stable, continuous flow.
Exactly. But it's not just power. I mean, you need an absolutely massive, highly stable electrical grid because AI processing consumes electricity on the scale of small nations.
Which is just wild to think about.
It is. Then you need a telecommunications membrane. The physical fiber optic glass threads buried in the dirt that connect those isolated servers to the rest of the world.
Right.
Then you need land. Millions of gallons of water for thermal cooling, and highly specific governance.
Governance? Like local politics?
Yeah. Zoning laws and regulations act as an institutional membrane. They allow these massive, super noisy facilities to operate near residential areas without being shut down.
When you lay it out like that, it sounds nearly impossible to pull off.
It's incredibly difficult.
So what happens when you actually successfully stack the power, the fiber, the land, the water, and the zoning laws, all in one specific geographic place?
When all those constraint membranes overlap and function together smoothly, they create something entirely new: computational connectivity.
Okay.
The sources emphasize something profound here. Capability is not the opposite of a constraint.
Oh, interesting.
Right. Capability is a local order that manages to exist stably on top of heavy physical constraints.
Oh, that's a brilliant way to frame it. Because we usually think of constraints as things, holding innovation back, red tape.
Exactly.
But this thesis argues that the capability only exists because a specific city has figured out how to master and integrate those constraints.
And that is why the integrated capability of the entire city matters far more than any single data center facility.
Because the building itself isn't enough.
No. A tech giant could build the most advanced server farm on Earth in a random town. But if the local power grid has a brownout during a heat wave,
Right.
or the local government suddenly blocks the water usage for cooling that billion-dollar facility, is just an expensive paperweight.
Wow.
Northern Virginia's superpower isn't just having big buildings, it's having a deeply integrated, highly functional OS layer that can absorb and sustain global computational demand without collapsing.
It's the entire ecosystem. The city itself is the machine.
Exactly.
But, this division of labor terrifies me a little bit.
Why is that?
Because if Northern Virginia is doing all the heavy lifting, we have to look at the other side of the equation. We have to look at San Francisco.
Oh, right.
How do these two totally different environments interact on the global motherboard?
That interaction is exactly what the COA thesis dissects. If we use the LMOS framework to look at their operational speeds, we see a stark, necessary division of labor. San Francisco functions as the center for experimentation, startup culture, and conceiving the future. In the language of our sources, it operates at a very high narrative speed.
Narrative speed.
Yeah. It is entirely about direction, intention, pivoting, and fast-paced ideas.
So San Francisco is the software developer, writing the code, pitching the grand vision to investors, adopting the whole move fast and break things mentality.
Yes. But Move fast and break things is a catastrophic philosophy for a high-voltage power grid.
Yeah, no kidding.
Northern Virginia, conversely, functions as the long-term computational supply hub. It operates at physical reality speed.
Physical reality speed.
Right. It deals with the slow, heavy, immutable realities of logistics, laying miles of copper wire, acquiring real estate, thermal management.
So if San Francisco is envisioning the future at light speed, and Northern Virginia is physically sustaining it at the speed of pouring concrete,
Yeah.
isn't there going to be a collision? Like, what happens when the software outpaces the hardware?
That collision is the central vulnerability of our era, which is what the second half of our source material dives into. Modern civilization emerges from this specialization, but it creates a massive structural risk.
Here's where it gets really interesting, because that structural risk is playing out right now.
Oh, absolutely.
The demand for AI isn't just growing linearly, it is exploding. Every single Fortune 500 company on Earth is trying to integrate generative AI into their workflow, like tomorrow.
Yeah.
The computation factories are running red hot. So structurally, what physically happens to a hub like Northern Virginia if we push it beyond its capacity?
Well, to understand the physics of that failure, we turn to the MCP, or membrane contact phase model.
Okay.
It is an analytical framework used to measure dynamic stability in complex systems. And the MCP model completely upends a core assumption modern businesses have about efficiency.
How so?
In corporate culture, we tend to think that a perfectly synchronized, highly efficient system is the ultimate goal.
Right, 100% utilization, no wasted energy, no servers sitting idle, no downtime. I mean, if you're paying for the hardware, you want it running at maximum capacity 24/7.
Exactly. But the MCP model argues that perfect synchronization actually destroys long-term adaptability.
Wait, really?
Yes, the model focuses on two critical factors: thermal dissipation and metabolic reserve.
Okay, let's avoid the textbook definitions for a second. What does that actually look like in a data center? Are we talking about the ability to shed heat and having, like, emergency backup energy?
Essentially, yes, it is the slack in the system.
The slack.
Right. If an entire city's infrastructure, its power grid, its water cooling capacity is pushed to the absolute limit to achieve 100% efficiency, it loses its recovery capacity.
Oh, I see.
The time, energy, and resources needed to cool down, fix errors, and recover from external shocks just disappear.
I see. It's like running a nuclear reactor without control rods.
That's a great way to put it.
Like, sure, pulling the rods out gives you absolute maximum power output, which looks great on an efficiency spreadsheet.
Right.
But the moment there's a slight fluctuation in heat or a minor coolant issue, you no longer have a mechanism to slow the reaction down. You don't have the buffer to manage the spike, so you just melt down.
That is a highly accurate physical metaphor. And the MCP model details a very specific, dangerous phase that a system enters when it is pushed too far without that buffer.
What's it called?
It's called chronic depolarization.
Chronic depolarization. How does that physically manifest in a hub like Northern Virginia?
Let's walk through the mechanics of it. Imagine the data centers are running at 99% capacity to train a massive new AI model.
Okay, running red hot.
Right. Then a localized heat wave hits the East Coast. The physical facilities suddenly require 20% more power just to run the massive air conditioning units to keep the servers from melting.
Oh, wow. Okay.
But the local power grid is already operating at maximum capacity.
Right, because there's no slack.
Exactly. Because there is zero metabolic reserve, the grid's voltage begins to dip. To prevent a total blackout, the data centers have to instantly throttle their servers.
So a weather event in one Virginia county suddenly causes API latency spikes for software developers in San Francisco and users all around the globe.
Exactly. But it goes deeper. In a state of chronic depolarization, the system hasn't entirely collapsed, but it's operating in a permanent state of high friction and microsensitivity.
What does that mean for the people running it?
It means the maintenance crews don't have the downtime to replace degrading copper wiring. The local water utility is constantly strained.
It's just redlining constantly.
Yeah, the infrastructure is too exhausted to adapt to anything new. It just fiercely, rigidly maintains its current state, overreacting to the slightest stimulus.
I'm trying to wrap my head around the implications of this. If we demand so much AI processing that we constantly max out the local power grids and water supplies in these specific hubs, the system enters chronic depolarization.
Yes.
It can't grow, it can't adapt, it's just brittle.
If we connect this to the bigger picture, this is the true reality of the AI race.
Okay.
The public narrative, driven by that high narrative speed we talked about, is entirely focused on Who can write the better algorithm or release the smartest software model?
Right. The code.
But the structural OS layer tells us the real competition is physical.
Mm.
The winner won't just be the one with the best code. It will be the one who can sustain computational connectivity without burning out their physical city hubs.
Wow. So the actual bottleneck for the future of artificial intelligence isn't a math problem.
No.
It's whether we can keep the air conditioning running in suburban Virginia without crashing the local power grid.
That is the stark, unvarnished truth. I mean, the MCP model explicitly states that unrecoverable, high-efficiency systems will inevitably transition into a state of chronic depolarization.
It's inevitable.
Right. Perfect synchronization increases short-term efficiency, but it sacrifices long-term adaptability. What these models are telling us is that fluctuation stability, having redundancies, having downtime, having physical breathing room, is mathematically superior to rigid perfection.
It's the difference between a system that is brittle and one that is resilient.
Exactly.
And that brings up a concept from the sources that really stopped me in my tracks. They use the word care.
Ah, yes.
Now, usually when you're reading dense engineering texts about tech infrastructure and thermal dissipation, you don't see the word care,
You really don't.
but the text redefines it entirely.
Yes. The text explicitly states, care is not an emotion, it is a repolarization infrastructure.
Repolarization infrastructure. So if depolarization is that state of being maxed out and brittle, repolarization is the act of restoring the buffer.
Exactly.
So they are saying care is an actual physical necessity.
It means that maintaining a system, allowing it to rest, to cool down, to recover its metabolic reserve, is a structural requirement for civilization to survive.
Wow.
In this context, care isn't a feeling of empathy. Care is the physical maintenance crew replacing a worn-out server rack.
No.
Care is the urban planner intentionally designing a power grid with a 20% reserve margin instead of running it at 100% for maximum profit. Care is maintaining the flexibility of a system so it can absorb shocks without cascading into failure.
That reframes everything. It's treating the physical world with respect, recognizing that it has hard mathematical limits.
Yes.
We can't just keep hitting refresh on our browsers, expecting infinite, instant AI generation without consequence.
No, we can't.
Every single query you type into an AI chatbot has a physical cost. It generates physical heat. It consumes physical water.
And that cost is paid by these quiet, specialized cities that most people never think about.
This has been an incredible shift in perspective. I mean, we started by challenging the illusion that our digital lives live in a weightless cloud.
Right.
And we've seen that structurally, the digital world is incredibly heavy, anchored deep into the ground. It depends entirely on physical constraint. Membranes, power lines, cooling systems, land use regulations.
And the survival of that entire global digital system depends on not driving those local physical hubs into a state of chronic depolarization.
The most vital civilizational functions, the ones literally keeping the global motherboard running, are located in places like Northern Virginia that receive very little public attention.
Exactly.
It's not just about the flashy software being coded in San Francisco. It's about the heavy physical supply chain of computation that must be carefully structurally maintained.
This raises an important question for all of us. If capability is defined by successfully operating on top of physical constraints, how many other invisible supply chains were we taking for granted simply because the narrative layer hides them from us?
That is exactly the kind of cognitive cooling we needed today, piercing through the hype to see the structure underneath.
Yeah.
Which brings us to the end of our deep dive. But we want to leave you, the listener, with a final thought to mull over. We asked you at the beginning to look at the world differently, seeing cities not as places on a map, but as civilizational functions on a global motherboard. So, as you go about your day, look at your own city. If the map was stripped away, what hidden function is your city quietly providing to the global operating system?